Hello everyone. So this video will cover setup and hold timing analysis. There are two reasons why we are introducing this particular topic over here. The first reason is obviously it's a basic VLSI frequently asked question in VLSI interviews. That is the first reason. And the second reason is we want to understand the behavior of on-chip variation, that is OCV, that we discussed some time back. So these are the two reasons that we are bringing this topic over here. So let's begin with the setup timing analysis. What we'll do is we'll take initially the ideal clocks. By ideal clock we mean that the clock tree is not yet built, and then we'll do a timing analysis with the ideal clocks first to understand what are the basic structures and what are the basic parameters that we need to get used to, and then we will be introducing the real clocks and then doing the timing analysis again. Okay, so let's begin a setup timing analysis with ideal clocks. So, and it's also single clock. So there are scenarios where your launch flop is triggered by some clock and your capture flop is triggered by some other clock. So let's now focus on a very basic and simple scenario of a single clock. Okay, so this is the specifications we have. The clock frequency is being given to us as 1 nanosecond or as 1 gigahertz. So the clock period, which is inverse of the clock frequency, is 1 nanosecond. So we have this launch flop which is sitting over here, we have this capture flop which is sitting over here, and we have this combinational logic which is between the launch and the capture flop, and we have the clock network, which is in this case it's the ideal clock network. When ideal clock network we say that it's the clock tree is not yet built. When the clock tree is built, you will see a lot of buffers in this path, but right now the clock tree is not built yet, so it's an ideal scenario. Okay, and this is a typical scenario for identifying for a setup timing analysis and hold timing analysis. This scenario is a very typical scenario. So let's move on. For example, we'll take, this is the clock period of 1 nanosecond. This is your 0th edge and this is your 1 nanosecond edge. Okay, and this is the clock period from 0 to t. Okay, so in a basic setup timing analysis, what happens is you send this particular edge to the launch flop. Okay, and the other edge to the capture flops. But let's try to let's try to put it in a more graphical way. And this particular edge at this particular time instant, this particular edge reaches the launch flop clock edge. So let's put an arrow over here. Okay, so this arrow on the time axis says that on the 0th clock period, on the 0th time, there is one clock edge which reaches to the launch flop. Okay, and on the tth time period, which is at 1 nanosecond, at t equal to 1 nanosecond, the second edge, the next edge just to this one, the second edge reaches the capture flop, and this is, let's put the arrow over here. So whatever analysis we have to do between 0 and t, that is between this, in this particular area. Okay, so with that said, let's assume that the combinational delay between the combinational logic has got a delay of theta. Okay, and the setup timing analysis says that if for this particular combinational logic to work, or for this particular circuit to work, your combinational delay, which is right from launch flop, the internal delay of the launch flop to and the combinational delay over here, that should be less than the time period. And it's pretty obvious, because if the combinational delay which is present over here exceeds the time period, for example it was t is equal to 1 nanosecond, and if your combinational delay is 1.5 nanosecond for example, then your clock period has to be shifted to more right hand side. Your clock period will become 1.5 nanosecond, and your clock frequency will reduce from 1 gigahertz to 1 divided by 1.5, roughly around 800 megahertz. And the reason is, as you increase your time period, your frequency decreases. It's a inverse ratio over here. Okay, so that can't be allowed, because the system has been designed to work at 1 nanosecond or at 1 gigahertz. So any activity that is happening, or any combinational delay between the launch and the capture, should be happening in a period which is less than 1 nanosecond, that is in a period which is less than t. Okay, so this is the first basic equation for setup time. It's just that the combinational delay, whatever you see over here, should be less than your clock period, that is t. So this condition is enough to say that this system will work at 1 gigahertz. But now we have to introduce more and more practical scenarios into this. Okay, the first practical scenario is the flop itself. So let's open up this particular flop. When we open up this particular flop, you see some combinational circuit over here. So this flop, the box that you see over here, it has got several MOSFETs, it has got several logic gates inside it. It's not just a black box. There are a lot of gates inside it, and there are a lot of resistances and capacitances which are present inside the capture flop. So let's look into a more higher level thing of this particular flop, that is a structure which consists of two muxes. So this is the mux1, this is the mux2, and the way a flop works, it will be more clear from this particular timing graph. So when your clock is at zero, okay, your D input, whatever it is present at the D input, or whatever is present at the D input, that reaches from this particular point till this particular point through this particular mux. So there is a delay associated with this particular transit of information. So your information moves from D to QM, and that takes an amount of delay which is equal to the delay of this mux1, because this mux1 is again built on various resistances, MOSFETs, PMOS, NMOS, and everything. Okay, so there is a finite delay that it takes for the D input to reach from this point to this point. And all this happens when your clock is equal to 0. And in this case, when your clock is equal to 0, the output is fed back to the input of the mux, and that is being driven. So basically output is not moved. Your output doesn't changes. When does the change exactly happens? When your clock switches from logic 0 to logic 1. So when your clock switches from logic 0 to logic 1, you see a logic 1 over here. When you say logic 1, the output of this particular mux is now fed back to its input, and this particular data just rotates over here. But over here, when you feed a logic 1, your QM, the data which is present at QM, moves from QM to Q. So again, there is a second delay that is associated over here. So there is a mux2 delay that it takes to reach from this point to this point. Okay, but the point is, why are we even looking into this? What all this thing will impact our setup timing? So that's exactly the point. So the point is the mux1 delay or the mux2 delay, when there is a clock, when there is a logic 0 on the clock or logic 1 in the clock, that will actually affect, or that will actually restrict your combinational delay requirement. So initially we have seen that the combinational delay theta was supposed to be less than t, but now things will change. Why things will change? Let's see over here. So when you see there is an edge that is coming over here, for example, let's capture flop clock edge. Okay, so when the edge at the t clock period reaches at the clock port, the capture flop knows that it will need some finite amount of time for input that is coming at D to bring it somewhere at the center of the flop, to bring it somewhere over here. Okay, so the capture flop is aware of that. It is aware that it will need some finite amount of time, which is mux1, which is a delay of mux1, for whatever input which comes at D to settle it properly at the center. So as a result of that amount of time has to be subtracted from the complete clock period T. So initially, if the complete clock period T was available, we'll bring it over here. Initially, if the complete time period T was available for combinational delay to settle, now the time period gets reduced because there is some amount of time before T that is needed by the capture flop for the input which is present over here to settle at the center of the flop, which is the mux1 delay. So that is the mux1 delay, and that mux1 delay is referred to as setup time. is referred to as setup time, which is mentioned over here. So let's put some setup time. So there is some finite amount of time which is required for the D input to settle from this point to the center of the flop, and that amount of time is referred to as setup time. So now your clock, so if the combinational delay lies somewhere between at this particular point, basically somewhere before this one, so the capture flop has got enough time to bring the data which is present at this point, which is present at the D pin, to the center of the flop. It has got enough time. It has got, that is basically is called as the setup time. It's called the flop setup time. So now your equation changes to the combinational delay requirement now comes, initially it was combinational delay should be less than t. Now it should be less than t minus s. It should be less than t minus s, where s is the amount of time required by the capture flop to settle the information which is present at d somewhere at the center of the flop, which is the mux 1 delay. Okay, so this is so we have brought one more practical scenario over here. So let's take an example. For example, if t was 1 nanosecond and let's say it takes only 10 picosecond of delay, let's say we are at a very advanced node and the capture flop takes only 10 picoseconds, so your combinational delay should be less than 1 nanosecond minus 0.01 nanosecond, which is 0.99 nanoseconds. So combinational delay should be less than 0.99 nanosecond. This will ensure that your system will definitely work at 1 gigahertz. Okay, so this was the first level of practical scenario that we brought into the picture. There are more levels of practical scenario that will be coming into the picture, but since I'm already running out of time, let's try to bring all those practical scenarios in the next video. Thank you.